Alright, so what we're talking about today is collisions. And what we have here is we got the two cars. And I'm going to push them together with equal speeds, and they're equal cars, so they got equal masses. So they're going to have equal momentum coming into the crash. So they come at each other, and they bounce away. And what happened right there was you could see with your eyes that their speeds were approximately the same coming into the crash. Their speeds were approximately the same leaving the crash, meaning their momenta were approximately equal. Now, here's the thing about it. The total momentum that all the cars have before the crash is going to equal the total momentum of all the cars after the crash. Let's try this again here. And you can see again. So let's talk vectors here. From your perspective, this is going to be a negative direction, and this is going to be a positive direction. And so you've got a, let's just give it a random number. Let's say it has a momentum of 100, and this one has a momentum of 100. Well, this would be a negative. So in the initial part of our equation, where we have the total momentum before the crash equals the total momentum after the crash, this one would have negative 100, this one would have positive 100. If you have those both on the initial side, then they're going to add up to 0. They're going to run into each other and bounce off, and now their momentum are going the opposite direction, both at 100. And so it's going to be 100 plus negative 100 equals negative 100 plus 100. And the big idea being that momentum is conserved in the crash. Now, if we change it up a little bit and I push one a little faster, one a little slower, you'll see the change there. I'm going to push this red one a little bit slower and this blue one a little bit faster. Slow, fast. And you can see immediately after the crash, the blue one was going faster, the red one was going slower, and then they switched. So it's like, let's say we had 100 units of momentum to split amongst them. In the beginning, maybe it was 70-30. After the collision, it might have been 70-30. The total amount of momentum remained the same, but it was shared unequally. Now, not only when we talk about these collisions do we need to talk about momentum being the same, we also need to discuss what's going on with energy. When we have an elastic collision like this where they're bouncing, that's one of the key factors for elastic collisions, is that they're going to bounce off each other. They're bouncing, there should be very little, well, in a perfect collision there should be no heat, there should be no warping, there should be no sound created. That's why in nature most of them aren't actually perfect collisions. They're often slightly this and that, but here we're bouncing, we've got the magnets, so we're calling it an elastic collision. In this case, kinetic energy will also be conserved. Now that's just to say that the kinetic energy before the crash is the same as the kinetic energy after the crash. Now if we turn my cars around, and we have the Velcro. We have the Velcro. Now, when they come together, they're going to hit, and they're going to stick together. And we're going to call this an inelastic collision. In inelastic collisions, there is going to be heat, sound, the deformation of the particles. While momentum will still be conserved, meaning we had negative 100, positive 100, totaling up to 0, because it would stop, momentum would still be conserved, but in this case, the kinetic energy is not conserved in an inelastic collision. Where they stick together, your energy gets used in other ways, whether that's heat or light or sound or the rearrangement of particles. When your car hits a telephone pole, the particles of your car are being rearranged. The particles of the telephone pole are being rearranged. Sound is created, heat is created. That takes energy, and that energy comes from the kinetic energy. So let's see a little example. I know you've seen this in lab before, but look, they come at each other and they almost stop. I pushed that one a little too fast, I think. But the total amount of momentum adds up to being the same. But the kinetic energy most certainly decreases. Let's try this one more time. And they stop because I had the same amount of momentum going forward and backward, negative, positive, adds up to 0. 0 before the crash, 0 after the crash. So I hope that helps you understand momentum and collisions a little better.